Alright, so here we're going to be covering just how to take the derivative of a function. Some of these functions are going to get a little complicated here, so it's a good review of all of the derivative concepts. And for those of you watching the video and wondering why the numbers are out of order, they're related to the problems on this review packet we're working from, and we're not necessarily doing these problems in order, we're just covering them sort of by topic. So question 6 says to calculate the following derivatives, do not simplify your answers. So don't waste your time trying to make these look nice. Just give the final answer an accurate derivative rather than a nice looking one. Okay, so we've got a function y equals x squared times e to the x, and clearly we can see that this is two functions being multiplied by each other, so we're going to need to use the product rule here. So let's quickly review what the product rule is. So I would say if we have a function where y equals f times g, where g and f are functions, then the derivative is g f prime plus f g prime. There is a different order you could write there as well, but the reason we put it in that order is so that with the quotient rule, things aren't as different as they could be if you remember them as totally different formulas in different orders. So anyway, let's first identify here really quickly, what is our f function? Well, in this case, f is x squared, and our g function is e to the x. So that would make f prime 2x, and g prime is going to be e to the x. Alright, so let's just set this thing up then. Our final answer is going to be y prime equals g times f prime plus f times g prime. And I could leave it like that. It doesn't have to look any nicer than that. You may be tempted to rewrite it as 2x e to the x plus x squared e to the x. That's fine, but it's not necessary. Okay, B. If f of x is x squared minus 1 divided by x cubed plus 2x, then what is f prime of x? So this is not a situation where we are multiplying two functions together. We are now dividing them. So we're going to want to use our quotient rule here. And our quotient rule says that if you have a function where you have two functions being divided by one another, then the derivative is low times the derivative of the high function minus the high function times the derivative of the low function over the low function squared. And we remember that as low d high minus high d low over low low. But there are a lot of different ways to remember this. So let's go ahead and write out what f and g represent in this situation. F is x squared minus 1. G is x cubed plus 2x. So then f prime is going to be 2x, and g prime is going to be 3x squared plus 2. So we can go ahead and come up with our derivative now. The derivative of f of x is going to be low d high minus high d low over low low. And it's about now that you're realizing that the do not simplify is a nice instruction to have been given here. Alright, let's take a look at C. So g of x is ln of cosine of x, and we want g prime of x. So in this case, we aren't dealing with a product. These two things aren't being multiplied. They're not being divided either. This is going to be a chain rule because we've got a composition of two functions. If I said, for example, that this u, variable u, equals cosine of x, then you would express ln of cosine of x as ln of u. So I'm going to call that my f function. All right. Well, ln of u has its own derivative. If you take the derivative of ln of u, that's 1 over u. But don't forget that we've also got this u function, which I'm going to call g. G is cosine of x, and it's got its own derivative, which is negative sine of x. So we've got all of these components that are bundled together here. So when we take the derivative of this composition of two functions, we're going to want to use the chain rule, and the chain rule says that I'm going to take f prime of g and multiply it by g prime. So that's what I need to do in this situation. So if I'm trying to find g prime of x, and this is a very different g than this is just to represent this interior function. In this case, I'm going to have the derivative of ln of x, which is 1 over x, but in this case that's cosine of x, times the derivative of the interior function, which is negative sine of x. And I can put these two things together. You do not have to simplify this, but it should go without saying that this is a function we've seen before. But you could leave your answer like this. That's correct. It's just not simplified. Now example D. We've got a lot of components in example D. So initially, I'm noticing that there is going to be a product that we're dealing with here. We've got x times arc sine of 1 over x. Now within arc sine of 1 over x, we've got a chain rule here because this is a function on the outside of a function on the inside. So there's a product rule, there's a chain rule. We're also going to have to remember how to take the derivative of 1 over x, which doesn't necessarily have to involve a quotient rule, but if you want to approach it from that direction, you could. So let's first approach the product rule here, the outermost rule that we're going to need to deal with. So I'm going to call my f function x, and I'm going to call my g function arc sine of 1 over x. This is going to be an easy derivative to take. The derivative of x is 1. The derivative of my g of x function is going to be a little bit trickier because I've got to remember the derivative of inverse sine. So the derivative of arc sine of anything is 1 over the square root of 1 minus that thing squared. So in this case, that thing is 1 over x. But remember that because it's a chain rule, I need to multiply this whole thing by the derivative of 1 over x. And so when I do that, I'm just going to think of 1 over x as x to the negative 1. And when I take that derivative, that's going to be negative x to the negative 2, which is negative 1 over x squared. So I'm going to multiply this by negative 1 over x squared. So let's go back to using the product rule here to finish this out. So we're looking for h prime of x, and it's going to be g times f prime. So g is arc sine of x, or of 1 over x, times f prime, which is 1, so I don't need to worry about that, plus f times g prime. And g prime is that complicated expression over there. So we have negative 1 over, and I'm going to put this together, x squared times the square root of 1 minus 1 over x squared. And this is a very ugly looking thing, but remember they said do not simplify in the instructions, so we'll leave it alone. There is some stuff that we could do to simplify this, obviously, and one immediate step jumps right off the page. If you put the x there, then you can cancel those, but we don't have to worry about doing that right now. Okay. Next example here, we've got a kite that is 100 feet above the ground, and it's moving horizontally at a speed of 10 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string is let out? So we've got a related rate situation here, and it's always helpful to draw a picture of what's going on. So a kite is up in the air. We'll say that this is the kite. I'll use a color. Kite in the air, and it's 100 feet above the ground. We also know that it's got an angle with the ground, right? Because that kite is flying at an angle, and the length of the string we're saying is 200 feet. So the angle between the ground and the kite is obviously a right angle, and we do not know what this angle is. But we do know that as this kite's string is being let out, the kite is traveling horizontally, and we're told at a rate of 10 feet per second. So we know that that distance is changing. This lower side here is changing at a rate of 10 feet per second. And as that happens, this is being let out. So right now, in this moment, the kite is traveling 10 feet per second horizontally, the string is at 200 feet, and it's 100 feet above the ground. So let's identify a couple of things here that we know and that we're looking for. We can make this distance here x, and we'll say that x is the distance on the ground, horizontal distance on the ground. And so that means that dx dt, or the rate of change in x with respect to time, is the horizontal speed of the kite. Okay, we've got another thing here, which is this angle theta, and that's the angle between the string and the horizontal, or the ground. And so that would make d theta dt the rate of change of the angle between the string and horizontal. That's the thing we're looking for. At what rate is the angle between the string and the horizontal decreasing? So we're trying to find that. So what we want to do here is find a way to relate these components of things we know, things we're looking for, and the thing that we need to find. It would be a mistake here to go right to using the Pythagorean theorem, because you could find out what this length is when these lengths are 100 and 200, but that wouldn't help you find the rate of change of this angle. So what we want to do is somehow use that angle and connect it to x and some of the measures that we know. So immediately the thing that I'm thinking we could do here is we could use cosine of theta, because cosine is equal to the adjacent side over the hypotenuse. So in this case, then cosine of theta is going to be equal to x over 200. And so that means that x is equal to 200 cosine of theta. So what we've got here is a function x in terms of theta. What we're going to do now is try to use some of these things that we know, right? I know dx dt. So I can take the derivative of this function and I know what my left side of the equation will be equal to. So let's do that. So dx dt is equal to, well, if I'm going to take the derivative of the left side of this equation, if I want to look at it that way, I need to take this derivative as well. So what's the derivative of 200 times cosine of theta? Well, that's going to be 200. Obviously, we got a constant there. What's the derivative of cosine of anything? Negative sine of that thing. And remember, theta is not a number. It is a changing quantity. It's a variable. So this is a chain rule here. When I take the derivative of cosine of theta, I get negative sine of theta times whatever the derivative is of that theta, because that's a changing quantity. So now I've got an expression here that contains some things that I know. So dx dt is 10, right? We know this. 10 is the rate of change horizontally of this kite at that time, times negative 200 times sine of theta times d theta dt. There is another component here that we actually can figure out. Sine of theta is a value we can find, because remember, sine of an angle is equal to the opposite divided by the hypotenuse of the sides from that angle. So the opposite side is 100 from that angle, and the hypotenuse side is 200. So that makes sine of theta 1/2. So I could rewrite this then as 10 equals negative 200 times 1/2 times d theta dt, and this is going to help me find d theta dt, the thing I'm looking for. So now I know that 10 is equal to negative 100, that's half of negative 200, d theta dt, and now I'm just going to divide both sides by negative 100. Okay, so I could write this as a decimal, and I would say radians per second. There's no point here where degrees were mentioned, so we're working in the standard angular measure.